you'll need the pollen diagrams, handouts that show pollen records from 2 places in America. Okay, let's go. Now, pollen is interesting stuff. As well as being delicious on toast, it is, as any hay fever sufferer will tell you, massively abundant. Pollen it's almost ubiquitous. Wherever we have vegetation, we're going to find pollen. So if we look at fossil pollen, it should tell us what type of vegetation existed in the past. Now, pollen is tiny stuff, but the types of pollen that we find will reflect the vegetation, the community that existed at the time that pollen was deposited. And as we could guess, the vegetation community will change in response to climatic change. This is a scanning electron microscope image of pollen grains. They are extremely small and they're remarkably robust things. The only thing really that destroys pollen is oxygen. They will break down in oxygen. But if they're deposited in an anaerobic environment, they actually preserve very, very well. You can also see that there are distinctive shapes, distinctive forms of pollen that can be recognized under a microscope, and the types of vegetation that produce those different shaped pollen grains can be identified. Now, the fact that pollen is so small and so abundant means that if we take a relatively small core of sediment, this is an instrument called a Russian corer, which is pushed down into soft sediment, say from a bog. It can be rotated through 180 degrees and pulled back out of the ground, and we get this long, continuous sample of the layers of sediment within that core. From that, we can extract the pollen. A relatively small amount of sediment, maybe a cubic centimetre or so, will give us plenty of pollen to be able to identify. That pollen then, once it's been separated out from the sediment in which it's found, can be put in a blob of oil on a microscope slide, and a fairly laborious job then of working your way systematically through the microscope slide, counting the numbers of the different species of pollen grains you find in that on that slide, will give us an idea about what the vegetation community was like. Typically, you might count maybe a minimum of 300 grains, but that could be up to 500 or maybe even more grains if you want perhaps a more detailed picture. It is quite a laborious process, but we get some interesting data out of it at the end. Fossil pollen itself is a bit more battered than the fresh pollen I showed you earlier, but it is distinctive. And with a little bit of practice, you can recognize the key types of pollen, particularly tree pollen, that will enable you to make a reconstruction of the climate. Some of the common types shown here, daisy, hazel, has got 3 pores or 3 holes in the pollen. Pine then is a very, very distinctive shape of pollen. So you can see they're all recognizable. You can also see from the scale here on the top diagram just how small these things are. When all the data is collected, For each layer, what we'll have is a number of grains of each different species. Each layer then gives us a point on each of these graphs. If we look at those over time, so from each of the layers, we get a picture of the changing proportions of pollen that we find at different times. That's put together in this. This is a pollen diagram. This is how this data is represented. A pollen diagram is a number of different graphs. There's a different graph for each species. That graph shows the percentage of the fossil assemblage that's made up of each species at each level. So, for example, at 13,500 years, we can see we'll have a number for the amount of spruce pollen, a number for the ash, a number for the elm, a number for the oak. Okay, plus the other herb pollens as well. Put all those together, and we can see the change in vegetation over time. Now, the way that we then go about interpreting this is to split it up a little. We define what we call pollen zones. Now, a pollen zone is a horizontal line that divides this diagram up into periods of time where we have different vegetation communities. Now you can see this particular diagram has got some marked on already, labelled up A, B and C. Now personally, I don't believe, I'm not convinced by those. Let me show you the type of thing I mean. Okay. Because I'd like you to divide this diagram from Chatsworth Bog into zones. Now for me, my first zone goes from about 14,000 to 13,000 years. So I've labelled that up as zone 1. I tend to use Roman numerals for this, just habit, I suppose. That first zone is dominated by spruce, an evergreen conifer. There's a tiny bit of ash and oak, but it's predominantly a spruce forest. So that's where I'm going to draw my first zone. But at 13,000 years, I think the vegetation changes. Something else takes over and the spruce becomes much less common. So where would you draw your next line? Where would zone 2 be? Then where does that change again? Where would you put zone 3? I'd like you to have a go at this. But remember that this is it's an interpretation exercise. There's no one definitive right answer. You might find, well, I tend to find that this particular activity really shows the difference between lumpers in geology and splitters. Let's see what you come up with. Having done that first one, this is another pollen diagram from a different location in Illinois, Nelson Lake. Okay, I'd like you to zone this diagram as well, please. And then, what does that mean? What's this telling us about the vegetation in this area? How is it changing over this period of time towards the end of the Quaternary period? So, it's time to press pause and try and zone those diagrams. See what you can come up with.